So a black hole is just a region of space where you have so much stuff in such a small amount of space that it's so dense that the escape velocity is greater than the speed of light. And it shouldn't matter what kind of matter you have in that small amount of space. It could be normal matter, it could be dark matter, right? Well, it turns out that it might be a little bit more complicated than that. So the very first and only eureka moment I've ever had was when I was writing up my PhD thesis, and I had this result that showed that the supermassive black holes at the centres of galaxies might be proportional to the amount of dark matter that was also in the galaxy, what we call a dark matter halo that surrounds the actual galaxy itself. And I basically had this like moment where I was like, can black holes grow by accreting dark matter? And I didn't know the answer, and I basically had to just wander the physics department asking anybody that I could find that I thought might be an expert on this or have some piece of the puzzle so I could work out, what to say in my thesis about this possible result. So we don't know a lot about what dark matter is, but there is one thing we know about it, and that is that it's something we call collisionless matter. So you can have collisional matter and you can have collisionless matter. So collisional matter is like what you would expect normal particles of stuff to do if they were in like a cloud or like a box, right? So you can imagine lots of particles pinging around, and they're basically just going to hit into each other. And when they hit into each other, they exchange energy and momentum, and they basically communicate a little bit about, what the environment is like that they're in. So if you think about water in a pan on a stove, you're applying this heat to the bottom of the pan, and the water molecules close to the bottom of the pan start to get more energy, and they start vibrating more and more, and they'll hit into more particles, and then they'll exchange energy and momentum, and those will heat up and gain in energy. And so particles in the pan basically know about the local conditions. They know what the temperature and pressure and density is in the other areas of the pan, depending on whether they have more or less collisions. So compare that with collision-less particles. These are literally particles that just do not collide. It's not that they can't collide, it's just the probability of a collision is extremely, extremely low. So we say that their mean free path, so that's sort of the length that they can go without experiencing another collision, is much greater than the size of the fluid container that they're in, for example. And so the particles barely interact, and so they have no idea about the local conditions of the fluid that they're in. So they're very dependent on initial conditions and your starting point for how they behave. So that might sound quite a weird concept, but an example of a collisionless fluid of particles is actually stars in a galaxy. So if you imagine the stars are the particles in that sense, then really they're on orbits around the centre of the galaxy. There's no collisions between stars. So the sun, for example, has no idea what speed the other stars around it in the galaxy are going around the centre of the Milky Way. All it knows is that it's trapped in an orbit around some central black hole, which is not a local condition at all. It's a very, very far away object. And it's also based on the initial conditions of whatever cloud of gas formed our Milky Way, because that cloud of gas must have had some angular momentum then, and then as it condensed down and it started everything spinning, that's still the condition that the sun knows about, but it doesn't know about anything else in the system. So you might be wondering how in the universe we even know that dark matter is collisionless, because we know very little about it, and also we don't know what it's made out of. But it's actually something we've observed in the dark matter properties when we look out into the universe. So there's a very famous collision of two clusters of galaxies going on that we call the bullet cluster. So galaxies don't tend to be found by themselves, they're found in big clusters where they group together under gravity, and all of the space between the galaxies tends to be taken up by this big halo of hot hydrogen gas. So when two clusters collide, it's unlikely that the actual galaxies themselves in the cluster are going to collide, because, they'd have to be on extremely, extremely tight path, like threading a needle kind of thing. When in reality, they tend to pass each other by. So we look at the collision between these two clusters of galaxies. We use X-ray emission to trace where the hot gas is. And then we use what we call gravitational lensing to determine where all the mass, or the weight of all the matter, is in the image as well. So this is when we know that wherever mass is in the universe, it's going to curve space-time by Einstein's theory of general relativity. That means any light behind that big cluster of galaxies is going to get curved along its path away on its way to Earth. And so it'll act as like a gravitational lens. And so any little lensing events we see of galaxies in the background behind that cluster can tell us where all the mass is in the cluster. And so when we do that, we see that all the X-ray emission is coming from the gas that's collided and basically been left behind as the two cluster of galaxies passed through each other on this collision. All the stars are obviously have passed through each other, and then all of the mass is found tracing the stars and the galaxies in that collision. And so we know that the dark matter must therefore also be collisionless, just like the stars and the galaxies. But what does dark matter being collisionless mean for supermassive black holes trying to grow by accreting dark matter? So if you imagine a black hole just sitting there happily, and you imagine some normal matter, some gas, like falling onto the black hole, what's going to happen is that as it falls onto the black hole, it's not going to be on the perfect trajectory to just take it straight into the centre. Gravity is going to get involved in a little bit, and it's going to travel on a curved path and settle down into what we call an accretion disk. So a disk of material that eventually the black hole will accrete. And so in that accretion disk, the outer regions will actually be travelling slower than the stuff closer in, just because of the fact that it's got a longer path to go and it's not as affected by the gravity of the black hole as much. But for stuff closer into the black hole, as long as it's not past the event horizon, that point of no return where it can't escape anymore, it's just going to be on a really fast circular orbit and has enough energy to just stay there. What needs to happen is for it to lose energy somehow and to reduce its orbit enough so that it passes that point of no return. How it does that is by transferring energy to other particles in that accretion disk by collisions. So instead of gas, if you can imagine a clump of dark matter coming in, that same process is not going to happen. It's not collisional, it's collisionless. And so the process by which you need to remove that energy or the angular momentum it has from going around in a very fast circular orbit, it can't have those collisions to transfer the energy outwards, and so it will never reduce its orbit in order to be accreted by the black hole. So that way that accretion happens around a black hole is obviously all purely theoretical, but what we've managed to do is confirm that idea with our observations as well. So this has been done quite recently by Hopkins, Richards and Hernquist in 2007, where they looked at something called the Quasar luminosity function. So quasars are basically growing supermassive black holes. So the hydrogen gas, the normal matter that's in that accretion disk around them, gets very hot due to friction, and then it starts to glow, optical, X-ray, UV, kind of across all the spectrum. And then we can see that, and we can see the accretion disk around the black hole, so we know that it's currently active and growing. And so a quasar luminosity function is basically looking at the numbers of extremely bright quasars and the numbers of more fainter quasars at all different times or redshifts in the universe. And so if we know how bright they are, we know how much mass they're actually going to accrete. And then we can compare that with how massive we know supermassive black holes have grown to be. And so we can say, does that amount of brightness account for how big we now know supermassive black holes are? And so what Hopkins and his collaborators found was that actually, yeah, most of the mass in supermassive black holes can be explained by the brightness that we see. And so most of the mass being accreted by supermassive black holes must come from normal matter that we can see because it heats up and glows as it's being accreted. The thing is though, those observations are obviously going to have some uncertainties about them, especially because the more distant things you look at, you know, they're fainter, so our observations are a little bit harder to do, they're less precise. And so what we need to do to confirm that result is also to run simulations of this very thing happening on computers. And the cool thing about simulations is that it can try and put some percentage or a number on how much normal matter and how much dark matter is accreted by a black hole over its lifetime. So one group to do this was Peirani and De Freitas Pacheco in 2008. And they basically said in the ideal circumstances, when everything is sort of rosy, you can get up to 10% of all the matter accreted by a black hole in its lifetime is dark matter. only up to 10%. In reality, it's probably going to be less than that because that idealized the whole situation. Because this is just how black holes grow, you also have to consider what happens when they form as well. So normal black holes that just form from after when a massive star runs out of fuel and then the sort of core collapses down into a black hole, you know, that is going to be mostly normal matter. You've had mostly normal matter in the star itself as well. But what about the first black holes? The first black holes that we think formed in the very early universe. So some of you might remember my video on direct collapse black holes in the early universe. So that instead of making sort of a black hole that was maybe 10 times the mass of the sun after a big supernova in a star that ran out of fuel, you could make something that was 10,000 times the mass of the sun to seed the formation of supermassive black holes that could grow to 1 billion times the mass of the sun at the centre of galaxies. And so people have been wondering, when that process happens, do you get dark matter collapsing into the centre of the black hole? But you also have to consider the properties of dark matter and normal matter again in that scenario. So normal matter, when it clumps together under gravity, also has electromagnetic forces acting on it. So magnetism and electric forces, they're going to be positive and negative, that basically make it a little bit sticky, making it more likely to clump together more and more and collapse down either into a star or into a black hole. Dark matter, though, doesn't have that. So it can clump, but then those clumps can disperse. And so it's a lot more diffuse. That's why you get those diffuse halos around galaxies as well. But obviously, if you have that baryonic matter collapsing down, then perhaps also you're going to trap some dark matter in the centre of it as well. But considering how dense that normal matter has to get for the collapse to occur, it's more likely that there's going to be a much higher percentage of normal matter than there is dark matter in that very first collapse of material down into a black hole. So I'm going to let you in on a little astrophysics secret here, and that is, if there's an astrophysics paper published in a science journal, and that paper has a question for its title, the answer is usually always no. And I think that's true of YouTube videos as well, especially ones on my channel. But here I think the case is more of a maybe we don't know. Until we understand what dark matter is and what it's actually made of, then we can't model this or simulate this properly or understand the observations fully that we're seeing either. So we really need particle physicists to just hurry up and figure out what dark matter is already, because we all really want to know. So it turns out both of my mics are out of battery, and I don't know how this happened at the same time, but basically Karma hates me. That it's so dense that its escape velocity is greater than today is bad, by running simulations on computers of this very thing happening. Oh my god, what is it with motorbikes in the street? And so we think dark matter is collisionally... Oh, that's like the first time I've done that now. Collisionless, collisional, collisionless, collisional, collisionless, collisional, collisionless, collisional, collisionless, collisional, collisionless.